Recording. Okay. So welcome everyone. Thank you all for coming. So this will be the sixth talk of this seminar, and I have the pleasure to introduce Pierre-Cyril Aubin-Frankowski, who is going to talk to us about his work in gradient descent and gradient floats with general cost and EVIs, I suppose. So, Pierre.
Okay, thank you, Francisco, for the invitation. Thank you for everyone for joining. Do you have like a black box on my screen, or you see it like a full slides?
I see perfectly, like the full
Okay,
slide.
that's good. Okay, so I will be talking to you. I got what for 50 minutes and then questions more or less.
Yes.
Okay, I will target that. So, I will tell you about something that's been occupying me since by now 4 years, more or less. And essentially, it's in two works. One with Flavien Léger, that was first in discrete time. And then we moved to continuous time with Giacomo Sodini and Ulisse Stefanelli at University of Vienna, where I was a postdoc until like 1 year ago, almost exactly. And since then, I've joined École des Ponts et Chaussées in Paris, and I'm a researcher at CERMIX, which is the lab of applied mathematics in this engineering school. So, um, I will be talking about gradient flows, but not only in continuous time, but it's one good way of entering the topic. So let's say, for simplicity, that we're in a Hilbert space, and you have this gradient flow, and you would like to study its properties. If you want to connect it with some time discretization, we know that the very accurate one would be implicit Euler. So just one way of possibly discretizing in time this equation. And we know that it's related to the prox operator just by first order condition. So this is good whenever we are in Euclidean or Hilbert spaces, but if we are in a metric space, then you pick up your favorite book, the Ambrosio Gili Savare, you suffer a little, you replace the Hilbert distance by square metric, and that's it. You then start studying this version of gradient flows. You no longer have this connection, or there is a connection with something called like related to subdifferential, but I will talk only very briefly about it later. But basically, you cut this connection and you start studying directly the implicit scheme. And what we did was, do we really need a metric structure or underlying? If I give you a cost function, think of a Bregman divergence, the Kullback-Leibler, and I would like to regularize my function with it, then what do? Well, I just replace the d squared divided by 2 by this cost function. And you have to have in mind that this cost function can be almost anything, but among the good properties it should have is like non-negative and some kind of being non-degenerate. So that's like the prototype typical cost function. My cost functions will be always based on properties of squared metrics. They will never be inner products, for instance. So cost functions for me are kind of like metrics. And so we did this paper with Giacomo and Ulisse. That was like last year in May, and so we're still waiting for the review, but it was a work that I was very excited about. Why so? Let's start with some examples in the metric setting. Imagine you have the quadratic function, here represented with the level lines, and you would like to do a scheme based on a metric. And the metric, you take an LP metric. This is an image I took from Gabriel Perret. And so basically you just say, I don't know which P is good, and I try several of them. You see that the trajectories are completely different in kind of shape and where the points accumulate as well, depending on whether P is infinity, 1, or equal to 2. Even for the quadratic function, of course, you're regularizing it with an LP, so it's maybe not the most naturally connected norm. What is the rate of convergence of this algorithm? Is there some kind of property of uniqueness and conduction? This will depend on the couple or the interactions between phi and the metric that you use for the regularization. In particular, if you are in the PDE setting, so sometime before 1976, and a very well-known result, if you have the heat equation, you want to discretize it in time and want to give a variational understanding of one possible discretization, you can consider this one, which is like a prox operator of the Dirichlet energy with the L2 norm. How to go back, you just take the gradient with respect to rho, and you will get the discretization in time of the heat equation, and you just have to prove that you're allowed to take the limit when tau goes to 0. And then the foundational result, I would say, of a whole branch by now of like applications of optimal transport is to notice that the heat equation is also the gradient flow, but for a different couple of functional and metric, the functional here being the entropy and the other being the Wasserstein 2 metric. I will not focus specifically on Wasserstein 2, but you can just consider it's one of the costs that I'm allowed to consider. It's a cost that is too simple in a sense because it's just a square metric already. But if you have never seen Wasserstein 2, just the difference and why is it between those two equivalent schemes with the heat equation, only of course in the limit when tau goes to 0, is can be kind of summarized in this picture. Suppose I have the density of mass yellow and I would like to move it to the dark purple, and I look for the geodesic in either the L2 norm or the Wasserstein 2 that brings me from yellow to purple. If I'm in the L2, then my geodesic is just the convex combination. And for two masses, it means I destroy progressively the mass on one side and I make it appear on the other side. Whereas for the Wasserstein 2, that's very well known. I'm just repeating like foundational results, but that are already like more than 20 years old. The idea is you don't teleport the mass, you only move it in the plane. So which is much more physical in terms of interpretation. You have a push forward map that is moving your particles progressively. And the entropy is rather more physical energy than the Dirichlet energy, as in it's something you can easily interpret with statistical physics. So that's why it can be important if you have a given PDE or a gradient flow to have several different characterizations, because the convergence properties, what you can say about the flow, will be in general encoded in also the discrete time scheme. So why not study these couples? Now I will, so this is for the scheme, and I will recap the connection with the notion of evolution, variational inequality, and how do you do metric flows in like flows, gradient flows in metric settings. So the idea, the first point to notice is that this equation has no meaning in metric because you cannot talk about the derivative and you cannot talk about the gradient. So you have to replace them with other objects. I will do the proof first in the Hilbertian setting. So what do? You start by moving to a weak formulation where x is just some test point. And well, since I have something that is local, x prime equals minus gradient of phi, I can just multiply by some kind of direction, like take the inner product with a direction, which in this case will be xt minus x. So, okay, I've written that. The left-hand side, you can notice that it's the derivative of the square distance. And the right-hand side is something for anyone manipulating convexity, very natural to consider. So the equality on the left-hand side is just the derivative with respect to time of the square distance. Whereas on the right-hand side, well, I want to get rid of this gradient. So I will assume that my function is lambda convex, lambda being in the real. It's not only non-negative values, it can be also negative. And I will just bound my term in red by the term to do it. And that's great because now I get, if I forget about the red terms, I get a formulation that is completely metric. So I don't have to bother defining what is the derivative or what is the gradient. That's what people would do, for instance, in Riemannian geometry. But here we drop any notion of smoothness. So we just drop those. In the Hilbertian settings, though, if you assume this thing, that will be my definition of the EVI. So it's basically this equation where I've replaced the square Euclidean by just some metric. I move the lambda to the left-hand side. I get rid of the red terms because I cannot consider them in the metric context. And this is what I call an EVI, but it's nothing else than what's written in black above. Well, what's nice in blacks is that the first equality with red is always true. And this is basically saying that x prime belongs to minus the subdifferential of phi. So in the Hilbertian setting, for any function that is lambda convex, there is equivalence between being EVI, that is satisfying this inequality, or being a gradient flow, just by the definition of the convex subdifferential. So you haven't lost anything. In the metric setting, it's a bit different. You are asking more because you are asking for your function to be lambda convex. EVI is an old theme. I think I can trace it back to Bresis. Like the first work, I think, is around Bresis, and there were several Crandall, Pazzi, and a lot of important people back then. They had another name back then as well. Basically, if you want the more recent presentation of it, I would say this paper of Muratori Savary was extremely helpful for us for the theory in the metric setting. Okay, so what are we going to see in the rest of the talk? That a lot of discrete time descent algorithms can be written as an alternating minimization. I will show you what's the connection with the notion of gradient flow. The convergence theory for those algorithms stems from a notion of discrete evolution variational inequality that was not put so much forward, I would say, in the literature on these gradient flows. And that, at least for the EVI theory of gradient flows, there is nothing particularly metric. Like, drop the metric aspect, almost every result that you would like still remains true. Okay, so I will start from the discrete time because that's where I originally came from to this kind of topic. Then I will move to alternating minimization as just very well sound principle for optimizing, and connect it with something that we called gradient descent with general cost. And then I will come back to continuous time. So if you lose me somewhere in the alternating minimization, or if it's less of your interest, don't worry, continuous time will come back later. Let's start with very simple settings. I will assume everything is differentiable. We are in finite dimensions. Later on, I will drop all these kind of assumptions. And I just consider implicit gradient descent. Implicit gradient descent, you can actually see it as an alternating minimization of a very simple function of two variables. That is, I want to minimize g. How can I upper bound g? I can just add to it a non-negative function. The bound always holds. Then if I fix x prime and I minimize with respect to x and assume x prime is xn, well, then I get as first order condition equation 1. Now imagine I fix x, that is has become xn plus 1, and I minimize with respect to x prime equals xn plus 1. So basically those two variables, they're not very interesting per se because one is always equal to another with maybe just a plus 1 in the index. But what they are doing is they are a placeholder. The x prime is like a placeholder. It's like saying, okay, you moved your xn from x prime to xn plus 1 at x. How to revert it back? You just do alternating minimization. Okay, it will be a bit more interesting later on. So that's like this function of two variables. And now if you want to do the limit when tau goes to 0, I have just told you, okay, the flow for G convex, you can just completely equivalently express with this EVI. That was the computation I've done before. And then how do you obtain the EVI actually? What you do is a discrete formulation of it. So assume you know this continuous in time. How do you discretize time derivative? Well, I will just break it up with those two first terms and have a tau as my time step. And I will add a third term. Why do I do that? Well, there are several reasons. One of them is connected to a notion of cross difference. Another one is like saying it's a term that in the limit you cannot see anyway, because xn plus 1 minus xn is of the order of tau to the square. Tau squared divided by tau or the tau. So basically this thing, when you take the limit, you will not see it. But bear with me. You take this thing, you just expand everything. You expand the squares. You regroup a lot of like the square in x here, and the square in x will go away. Do you see my mouse, right? Yeah, okay. But the square in xn plus 1 will stay, for instance. So basically, this formula here is nothing else than this one. And if I apply the definition of the scheme, I only get gradient of g. So writing this complicated, like seemingly complicated object is nothing else than writing the convexity of g. Why is it useful? Well, if you've done proofs of convergence rates for optimization algorithms, that's what you all do all the time, because those two first terms, they are the ones that are telescopic. So basically, like a take-home message for me is, well, convexity is much less about inner products than about differences of Euclidean distances. In general, if you want to prove your convergence, maybe the convexity expressed with the inner product is shorter, but the one with the square, like the difference of square distances is longer, but it's more practical for the proof, and it has the good taste that it moves directly into the metric world, whereas, well, you would suffer a little when you start with the inner product. Another thing, you take this inequality, which when tau goes to 0, you expect that it will end up with the EVI, and you just forget about the first term. You move the second to the right-hand side and the gxn plus 1 to the left-hand side. So I've just reshuffled my terms here. This inequality has to hold for every x. So basically, this inequality is nothing else than saying that xn plus 1 is the prox. So my message here is, if I only knew the EVI in the continuous time, I don't even know what an implicit gradient is. I discretize in time this thing. Well, my time discretization will encode the scheme that will be perfectly suited for me to analyze and to then prove the convergence. If I do another discretization, I would get maybe another scheme than the one that is imposed by this condition. So basically, inequalities like this that are valid for all x, they encode your scheme. Okay, so that was for implicit gradient descent. What about explicit? I will use the convention that g will always be the function for the implicit and f the one for explicit. So here is the explicit case. We know that to have convergence of the norm of the gradient and not convergence of the function values, it's enough to ask for a smoothness, which is basically just saying that the step size is well chosen with respect to the Hessian of the function. So that's one possible way of writing it. The other possible way is so-called descent lemma, that is this equation 4, if you forget about this phi here. And it's saying nothing else than something about the Hessians if you're allowed to derivate twice. What does this thing say? Again, like before, imagine I fix x and I minimize with respect to x prime, then I will get equation 3 by first order condition. Now, if I fix x and I minimize, I fix x prime and I minimize with respect to x, maybe it looks a little complicated, but we know that we cannot do better than f of x prime, so at least we can just say, oh, let's put x equal to x prime. So again, you have a rather placeholder variable that is not super interesting, but it will be useful. Just bear in mind. So this is like the upper bound, and I want to stress that there is not much difference between implicit gradient descent and explicit gradient descent. Both of them are built on building an upper bound on the function. The one for implicit was for free. I added a non-negative function term, whereas here it's an assumption. Okay, before I've shown you a discrete time EVI for the, and I told you it's like the convexity of G. Well, basically we need a lower bound on F, and there will be a form of strong convexity. So at this point, I do a short break. I'm just rereading known results, but that's what will be driving the intuition later. Implicit only needs one lower bound on the function, and the upper bound comes for free. Explicit, you have to assume the upper bound, and you get the lower bound for the convergence rate. But convexity is only something to get the convergence rate. It's not something to either really define the scheme, and the scheme is only something that comes from the upper bound. And that's why you would get norm of the gradient goes to 0 even if you are not convex. So I would say it's something not stressed often enough. I would say that a lot of algorithms, and that's what I will show, come from building up upper bounds of the functions And the lower bound is just something if you want to study the flow, the rates, or this kind of things. Okay. At the time, I think there was no theory for the explicit case of the EVI, and I will give you one later. So, okay, so this was the super easy part. Everything is smooth, and what if we're not smooth? What if I give you this time set x that is anything? I give you two functions f and g. G is like the non-smooth part. That's why it's allowed to have infinity values. And I would like to minimize f plus g. You may think of a splitting scheme kind of thing. How do I do that? One principled way is like saying, okay, you give me this time an extra information. You give me a y set, can be parameters, can be equal to x, can be something else. And you give me a cost function that connects x and y, and that is kind of like a squared metric, but it can be a Fenchel Young gap, for instance, if y is the dual variable. So it's something that just connects x and y. And then I want to build a canonical upper bound. This is called majorization minimization in the statistics community, and also in optimization, of course, but I would say it's mostly the statisticians that have a focus on it. And the idea is, okay, G, I leave it alone because it's the non-smooth part. And instead I will replace F by C plus sup of F minus C. Okay, this object, it's always an upper bound. Just take x prime equals x. Those two vanish and you get f of x plus g of x. And why this thing and not like a Fenchel transform? Why do I have a plus in front of the f rather than a minus? Well, it has to do with a choice of sign that is important. And it's not a Fenchel transform because you have to think that C is something like a quadratic distance. It's related. It's like the Fenchel transform of the quadratic minus the function. But it's not important to have that perspective. You should rather, if you know some optimal transport, you recognize that this thing here is so-called the C transform. And if I take the infimum, imagine G equals 0, and I take the infimum with respect to Y, I would be doing so-called double C transform. And it's inf plus sub plus as a kind of structure. But instead of doing the infimum with respect to Y, I will not do it. I will keep my two variables. And I get this function that is an upper bound of f plus g that depends on an extra variable. Okay, what do I do then? I just do an alternating minimization. I fix xn, I minimize with respect to y. I fix x, I minimize with respect to y. I have y fixed, I minimize with respect to x. So it's a bit the same thing I was telling you before, except that this time, instead of like assuming I know what L smoothness is, and I tell you this is a good upper bound you should be using because, well, Taylor expansion, Hessians, and all. I just say, oh, there is a cost function that you would like to use to regularize. Here, this is an upper bound. Also, you see that it's something that is not really about topology or any notion of differentiability. It's mostly about minimizing functions. For the simplicity of the talk, I will assume they always exist and the iterates exist and are unique. Uniqueness is not that important. You would then have you will have to select correctly which of the iterates you want. We'll come back a bit to this later. I will always need at least existence. So there is some kind of compactness, like kind of assumption. And that's also why C is not an inner product, because if you imagine G is equal to 0, if this is an inner product, there is no chance that there is a minimizer unless X is compact. So that's why it's rather like a quadratic distance. Okay, to have a picture of what's happening, you are at Xn. You have a lot of surrogate functions that depend on the y's and that are above your function that you'd like to minimize, f, that is the blue. I took g equals 0 for simplicity. Then you just pick at xn the function that has the smallest value among all the reds. You only look at a slice of it. And you say this function will be the one parameterized by yn plus 1. Then I forget about the blue, I minimize the red. It should be easier to minimize the rest because it's like minimizing the cost function with respect to x doesn't depend on f this time. And I get the xn plus 1 and so on and so forth. Why is it interesting when I'm studying the minimization of f? It's because if there is no gap, if f is always the infimum of phi, then the two, when I take the extra infimum with respect to x, the two should coincide. So it means that minimizing phi is the same as minimizing f. So I haven't like to change completely problem. Of course, if there is a point where the two functions do not coincide, then there is no reason that the infima would coincide. Maybe they do, but basically it's like saying, at this point, I don't really see the function. I am actually seeing it, for instance, the smallest convex contained in it or something like that. Like I see a deformation of the function in blue. So there are good situations where there is no gap, and there are bad situations where there is one. At least for not changing the function. Okay, so this is the upper bound I've defined for you. Here is my scheme. Maybe you would rather like a scheme that is based on first order, like a bit easier to read, like with the gradients and everything. Okay, assume everything is differentiable. The second equation, it's very natural to take the gradient with respect to x. The first equation, well, maybe you think it's very natural to take the gradient with respect to y. There's a little caveat. It's the fact that FC is like is kind of like the differential transform, okay, up to signs and everything, but you don't want to take the gradient of the differential transform because it's an object that maybe you don't have at hand. So what we'll do instead is, based on this picture, if there is no gap, then the functions have to, the function in blue and the function in the red have to have the same gradient at xn, because otherwise one of the functions would go above or below the other. So it would be a crossing point. No, so since it's not, since we always have an upper bound, the gradients have to coincide. So that's what we will say. We'll use the envelope theorem, say that if there is no gap, then the gradients of the two functions have to match. So it means the gradient of this function with respect to x, not with respect to y, has to match the gradient of the function at xn. So gradient of c xn yn plus 1 has to be equal to gradient of f of xn. And that's what's written here. The second line, it's just you take the gradient with respect to x, and you get this. Now imagine that c is the usual Euclidean distance. Then this thing is nothing else than xn plus 1 minus yn plus 1 equals minus gradient of g of xn plus 1. So this becomes forward-backward gradient descent. So my whole talk about building up something very abstract, at least when it's instantiated to the specific case of Euclidean, gives you back the algorithms that you know. Okay, imagine that g is equal to 0. So you don't have this, the second one for simplicity, and that basically c is minimal on the diagonal and x is equal to y. So like xn plus 1 is equal to yn plus 1. So those schemes, you will not see the difference between x and y. You should just think that y is like a placeholder kind of variable. So you only get the first iteration, and then you will change the cost. So if you take the cost that is L, so L times the quadratic distance, then you just compute this one and you will get gradient descent. If you take the Bregman divergence, I put here the definition if you have never seen it. It's a generalization of the quadratic, one possible generalization of the quadratic distance, because if u is quadratic, you get the quadratic distance. A typical one is the Kullback-Leibler, super useful functional. And you take this thing, you take the gradient with respect to x. Okay, it's you get gradient of u of x minus gradient of u of y. So those are those two terms here. And you basically get so-called mirror descent. If you take the reverse Bregman divergence, so I commute the role, and I take the gradient with respect to x. So careful, that means taking the gradient with respect to y in this expression. Well, I will get a Hessian from derivating with respect to y. Things simplify, you get so-called natural gradient descent, which is a special case of Riemannian gradient descent when you have a Hessian added. In particular, if you take u equals f, you get the Newton step. If you take L equal to x minus y, where L is a convex function, you get a preconditioner in front of gradient of f. If you take a Riemannian gradient descent, like going a bit beyond Euclidean vector spaces, then you will get this thing is nothing else than the definition of the Riemannian gradient descent. So as you see, a lot of schemes fall within this framework. The difference is it's not like I invent the scheme and then I find a quantity that will give it a variational flavor. Instead, I build something that is completely variational based on this. Variational, I mean that my iterates are based on argmin, and I deduce a scheme. Okay, that's good. That's the schemes. What about giving you a convergence rate? Okay, so this is the slide with the biggest novelty. That will be this notion of cross-convexity. You already seen something very much of the like. That was the discrete time EVI. I can jump very, very quickly to it. You look straight into the eye, into this thing. You say, okay, there is a plus, minus, plus. There should be a minus, but it's minus something equals 0. But basically, there are 3 to 4 terms on the left-hand side. And that's the same over here. Why is it a good notion? Okay, depends on your background. You maybe have seen something very much of the like. It's a lower bound on the function, so it's basically a bit like convexity. It's known as the 3-point inequality if you are in Bregman settings. It's the discrete EVI if you're in Riemannian case. If you have a Lyapunov kind of analysis of functions of iterations, it is, you can read it that way. The cross difference itself, why is it a good thing? You see that every term appears once with a plus and once with a minus. So if I change the cost function and I add a function that only depends on x or only depends on y, those terms will vanish out. So it tells cost functions, they only take care of which part of the cost does the interactions between x and y. Any function that depends only on x or only on y, gone, disappears. Okay, and here I've defined my iterates based on my scheme. I will change a bit perspective later, but that's the idea. So that's the lower bound. We need an upper bound. We are in the explicit case. Well, this time we take the so-called C-concavity because it's already off the shelf. And what does it say? It says there is no gap between f and its upper approximation. If the infimum is attained at yn plus 1, and that was what's required of the scheme, then you have to have equality. Think of something like saturation of the differential gap. It's really the same kind of idea. So you get this equality. And then what you do is you just take this one for any x and you instantiate it to a y that is yn plus 1. So yn plus 1, and you replace fc yn plus 1 by this thing, and you get this object here. Okay, so I have a lower bound on my function, an upper bound on my function. In the lower bound, you see that the two first terms are telescopic, so they are nice. This term, we think that it will be 0, because often enough, C is like a quadratic distance, and often enough, X and Y are the same iterates, so don't focus too much. This one, well, it will go away with this one. Okay, I will prove that it's not completely abstract concepts. I take the quadratic distance. I know that in this case, the iterates in x and y match. I know what's the iterate in x. And I just compute. So this one, what happens is any term that, like the quadratic part of the quadratic distance disappears because it vanishes with a plus and minus. So I only get minus the inner product. You regroup everything. You will get a xn minus xn plus 1 x divided by tau. Tau is my 1 over L. And basically, this complicated inequality with 4 terms, exactly like the computation I've done before, is just the convexity. The term above, I know that this thing is nothing else than the quadratic of this. I have to divide by tau, give me the 1 over L. I expand the first square, and I will get this. I put the f of xn to the right. That means that the upper bound I've just given you is nothing else than L smoothness, the usual one of convexity. So I'm creating abstract concepts, but they are the natural generalization of being convex and L smooth. What I will show you now is that if your function is C concave, or C-smooth, call it the way you'd like. Just have in mind that it's like saying that the Hessian of f is upper bounded, or that the function is upper bounded, and C cross convex, which will basically be convex, at least in the Euclidean setting. Then I can show you a sublinear rate just based on those two inequalities. And it's very natural because we know that's how it's done in the proof of gradient descent. Okay, there are also linear rates. There is also a possibility of having a local characterization. This is non-local because it depends on x and xn. If you'd like something based on the Hessian of f, if you have a meaning for it, it's possible. Okay, but this is not at all how we came up with this notion. We started from generic alternating minimization. So there is no cost function anymore. There's just a function phi that you would like to minimize doing alternating minimization. There are a lot of algorithms that fall in this category. You have alternating projections, you have synchrone, also known as IPFP, expectation maximization. And basically, Caesar and Tusnadi gave almost this inequality here, which on first sight looks like, why would I assume this on my function phi? It's true for the Kullback-Leibler and for x and y convex. But basically, this inequality is like my cross convexity will just be the instantiation of this inequality for phi that is C plus FC. What do we see about the inequality that is nice? Imagine lambda is equal to 0. We have phi of x y1 minus phi of x y0. Something is telescopic. We have something phi x0 y0. Okay, we don't know much about it, but we see something else. If I take x to be x0, the terms in 1 minus lambda vanish, and I get that y1 is the best y with respect to x0. If I now take y is equal to y1, I say that x0 is the best x for y0. So it's again an inequality that encodes the scheme. It says basically that those numbers, x0 and y1, which I just assume exist, have to be the ones given by 15. Okay. So with this inequality, what do we get? Well, even without the inequality, we are doing alternating minimization. So if we are at xn, yn, and I minimize with respect to y, I have to gain something. If I minimize with respect to x, I have to gain something. So it's a descent kind of algorithm, necessarily. If I have this inequality, I will show you have a 1 over n rate. And if you have better with lambda strictly larger than 0, then you will get a linear rate. What's the proof? Extremely simple. You just write your inequality here for lambda equals 0. And you want to create some terms that are telescopic. Okay, the first and the last, they are telescopic. Phi of xn, yn, well, it's missing something. So let's add phi xn plus 1, yn plus 1. And let's regroup the terms. And you get this. So I just added to the left and the right term. And now I see that those things in the brackets are telescopic. So I will sum. I get this. I know that I'm improving at every step. So the sum is larger than n times the last iterate. So this is this. I divide by n. The last term I can just throw because it's non-negative and there is a minus sign. So I get directly this. 3-line proof. Basically, that's what happens in, I would say, a lot of the algorithms that I've seen. Once you have shown or assumed the good inequality, the end is near. And this is a good inequality. Back then, Caesar and Tusnadi had given the formula. They have shown the convergence to the minimal value, but just as a limit, not with a convergence rate. And they didn't see the connection with other algorithms. So basically now, I give you as a corollary the whole convergence proof of gradient descent based on this 5-point, because I just say, if the 5-point is true, f is the infimum of phi, so that's why there is C concavity. I'm descending, and this descent inequality in red here, just rewritten, will give you this one. So basically says, well, f decreases, but if I take this one and I move to the left, I get something telescopic in f. I telescope. This thing is the stopping criterion in the norm of the gradient, because this term does not exist, like a 0, and this one is the norm of the gradient. Okay, and now if I add convexity, if I add convexity, then this time I get 1 over n rate or the linear rate. Okay, I will move to EVIs with the time that I'm left with. So I go back to this inequality, but this time instead of replacing phi by C plus FC, I replace it by G plus C, which was the implicit scheme kind of structure. And I write how it reads. That's this one. Okay, this thing actually appeared in Ambrosio in a corollary in the book. I will do a replacement. I divide by 1 minus lambda, and I call mu plus 1 to be this term. Why? Because it's nicer than having a 1 minus lambda thing. And I get this thing. And that's what I will call cross-concavity of the function. It's almost like cross-convexity, but you see there are 3 terms and not 4. That's because one of them is null. And what I will show now is what happens when tau goes to 0. Okay. So quickly on the gradient flow idea. So we've said that if you want to do it in metric spaces, I would recommend the book or subsequent papers. If we want to do it with a general cost, well, you can look at our paper. Um, Technical slide, but like just to say, focus on this thing that is called the energy identity. This is something true for a lot of notions of gradient flows, EDI, EDE, EVI. Those two you obtain by taking in integrating this one. I would just want to say I chose to focus on the EVI formulation because it's the one that requires the least prerequisites from gradient flows. It doesn't have to, you don't have to know what a metric slope is. You don't have to know what a metric derivative is. You just say, I know what this thing is, plus it's the strongest formulation. It implies the others. It gives you also uniqueness and contractivity. So it's a formulation that is quite practical. EVIs, well, they've been considered in a lot of kind of spaces, but also quite a few PDEs have been written as EVIs in their settings. So it's by now a very mature concept. But I would say that coming from finite dimensional optimization, I had not heard about it so much. So we have our cost function. I will take it non-negative. There has been some work in the metric case with asymmetric distances. I will focus on the fact that I don't have a metric, I don't have a triangle, and I don't have the continuity necessarily. What are the kind of costs that I'm interested in on measure spaces? One is the Kullback-Leibler, that is the relative entropy. Another one is so-called single divergence. So if you take epsilon equals 0, here you recognize the so-called Wasserstein C problem in optimal transport. Add this thing that is the entropic regularization. Well, then it's a nice cost function, but it has an issue. The self-transport cost entropic is positive. So that is OT of epsilon mu mu is positive. So what do you do to make it 0 on the diagonal? You just subtract the terms in mu and nu so that you make sure that this thing is 0 when mu equals mu, and it's actually non-negative under some assumptions on the cost as well. So those are the kind of functions that, well, this one is symmetric, this one is asymmetric. They are non-negative, but they clearly don't have any form of, they don't have a metric structure. So that's the kind of cost functions I would like to include in the theory. So here is a recap of EVI. So this is the EVI equation. The discrete time EVI is this form. And I told you it encodes actually the scheme under implicit Euler. What do I do when I move to general cost? Very easy. I just replace every d squared divided by 2 by a cost. That's it. And I can do the theory with explicit Euler, but I don't have time for it. So what do I need as assumption on the cost? Okay. Symmetry, but not always. It helps, but you can do without. We called it dissipative, helps as well, clearly. We can do either with, there will be some topology sigma, which can be the weak topology on measures, but either you assume that your function has compact sublevel sets with respect to sigma, or you ask some form of notion of Cauchy convergence. Basically, you will want to take limit of a discrete time scheme. You have to take some good notion of convergence. So either completeness or compactness. You want some notion of lower semi-continuity, otherwise no chance things will be true. It's something of this like, basically lower semi-continuity of phi and of C, jointly in general for C. The cross-convexity I gave you, and I will talk more about it. So cross-convexity, it's just you take the discrete EVI and you replace D squared divided by 2 by C, and that's it. And that's an assumption. Okay, now you can ask me, how do I check whether this assumption actually holds? Well, one way is so-called compatibility conditions. And that's basically saying, I will assume something on C, assume something on phi, then I will divide the second equation by tau, sum the two equations, and it will basically give me this first equation. That's like a bit of a mental play. Those two equations, so they already, of course, like appeared in the metric context. Here we lifted up to the cost functions. And I discovered that basically it's like saying you need not really a curve, you just need a direction at the point you are at, that is this point x1, such that the first function is like convex and the second function is one convex because there is this extra term over here. I can tell you a lot more about those inequalities. Basically, the second one you can think of, it's just the parallelogram, but where all the quadratic part in T I have thrown into the little O of T. But that I think there was quite some innovation in the paper to think of it this way. So this is a sufficient assumption for cross-convexity, or you assume directly cross-convexity holds. What do we show? We show this is the EVI. It's equivalently formulated in an integrated form. You take the integral of it. Or you can have also an exponential form. So that was basically a blueprint in the results of Moratori-Savary. Then what we show is if either compatibility or cross-convexity holds, then you will get an existence result of the flow because you will be able to build basically discrete iterates based on those and take the limit. Also, then there are the properties of the flow itself, independent of its existence. If the cost is symmetric, then just from the EVI, you can show that a notion of metric derivative exists with an h square that it's the natural scaling for the equation. And you can show that the time derivative of phi is equal to minus this metric derivative, like c derivative to the square. And that's just, it's within the EVI. And if you are in the metric context, I can recover you the fact that metric derivative equals to metric slope as well. And I was quite surprised because it's like saying, you look at the EVI and you wouldn't think that it encodes even the notion of metric derivative and metric slope, but it does. It does. It's okay. Then with the symmetry, you can also show contractivity. Both these results are valid for lambda that is possibly negative. So you like trajectories can go far from one another, but not faster than an exponential rate. But if you have lambda strictly positive, then you get all the results that we know for the traditional gradient descent or gradient flows. You get exponential convergence in terms of square distance, exponential convergence in terms of function values. If lambda is equal to 0, you will get the 1 over t convergence. And with some continuity assumption on the cost, you get stability for free as well. Voila. So what I've shown you, it summarizes two rather long papers, gradient descent and gradient flows. I've checked that it contains what was known in the metric theory, but I do not need to know the analog of metric derivative or metric slope beforehand. I can tell you there is not much metric in the EVI theory. You can do mirror flows typically with this kind of ideas. I find it very thrilling topic because well, there are new PDEs that could be maybe found, but yeah, if you're a PDE person, maybe novel schemes if you like algorithms. Maybe it tells you which kind of property you would like to have between C and the function phi, or C and F and G, and what's to be checked on a given practical basis. So we worked a lot with Flavien, and there's some other material on my website. And basically, those are the two articles. If you like the flow kind of perspective, I'd rather recommend the second one first. If you like algorithms and you like really a kind of step-by-step construction, you can check the first one. The first one is long. It's like 70 pages, but it's because of the formatting and blah. But it's also because we did a lot of subsections on specific algorithms. So if you like a given algorithm and you would like to know what's our perspective on it, you can check it out. Also, I have the opportunity to fund like a PhD on these topics. Can be 26 or later. I didn't check the audience, but I think it's most people are like more senior than prospective PhD students. But if you have good students that you think would like to live in France and work on this kind of topics, please write me. And yeah, with this, I conclude, and I'm happy to take any questions.
Thank you very much, Pierre, for this very interesting talk. So we can go right to the question, Luis.
Yeah, thank you. Thank you for the talk, and very interesting. I was wondering about, because in the last part, with some strong convexity, I understand you have convergence of the trajectory to a stationary point. But without that, in the Euclidean setting, let's say, or Hilbertian setting, you have also convergence. Even in the discrete setting, you have convergence of the trajectories, not only on the values. Then my question is about if you know some conditions that on the costs or that you are using, of the distances and you are using, that could you ensure also convergence of the iterate?
I did not put the result. I forgot to put it. If the cost is symmetric, you can show that the distance between the discretization and the continuous flow is smaller than tau times the constant. So we have a discretization error, and we can.
Symmetry is enough if in that case.
Yeah. So symmetry. Without symmetry, I cannot do it. I don't think so. I don't have counter examples. Also, of course, I'm always assuming kind of like the flow exists. That's like a sub note I didn't insist on, but like it's kind of like the cost function should behave locally like a square distance. If you try the cost function to be L1 or LP, well, it's just that it will be very hard to find functions for which it will be convex. So in some cases, you just don't have existence because basically these conditions fall. And the second one is typically a condition that has to do with parallelogram kind of structure. So if something is to be improved in that direction, yeah. Also, in terms of like convergence of the iterates, also in the discrete case, and not of the values of the iterates. Here we had a kind of a split with respect to a literature like Combet or this kind of, I would say, more very established convex optimization, because our set X could a priori be anything. So we don't have even a notion of what does it mean to converge in terms of iterates, but we can always talk about convergence in the values. So I have a bit this impression that in the optimization community, there are two groups, and you will never find rates of convergence in the book of Combet. So a bit similarly, you will not find in our case so much about the convergence of the iterates themselves.
Yeah, just the last, because with respect to the last part, you can actually don't have a rate of convergence, but at least convergence of data rates. Then the question was regarding that part.
Yeah. No, I completely get it. So what I can tell you is I have the discretization error under check. That's quite okay. The convergence of the iterates, we never particularly focused. My guess is there is some nice papers about Opial's lemma that will kind of give you a metric perspective on these things. So that would be the object to generalize to have convergence of the heat rates.
Okay, thank you very much. Yeah.
Cristobal?
Yes. Okay. Thank you for the presentation. Very nice results. I was just wondering that, in the traditional, let's say, convex optimization case in Euclidean space, you can obtain faster rates of convergence using different forms of acceleration. So do you have any understanding of what properties in this abstract setting might allow such faster rates?
I'm very much interested to do acceleration. I had a bit of a try at it and I didn't succeed yet. It's a tough topic. My guess is I'm basically focusing right here on this kind of schemes. So, and I'm giving to you a kind of scalar equivalent of this equation by giving you the EVI formulation. So if one wanted to do something a bit similar, maybe in acceleration, either you write the acceleration in this way with the augmented system with the moment, and you have to find a good EVI formulation for that. Doesn't exist to my knowledge, completely open. I don't think that this whole literature is really, I would say, pushed a lot by Savary and this kind of people. So I would say that they are not driven by a Nesterov kind of community. So that would explain why some things do not exist. There are some preliminary things. Among the technical issues is this can be already seen in this alternating minimization. We don't do extrapolation steps. We don't have the right equivalent for now. So that's also, even on the completely discrete time setting, we don't have the intuition. So it's possible, like, I would say that the Boyd-Condès paper kind of changed a bit perspective on acceleration in 2016, if you're familiar. And it's like saying, okay, you can either see it from the continuous time or from the discrete time. And the approaches, I would say, are quite different. So it's possible that both approaches will meet again. But we also know that even when known cases that cost is Bregman divergence, do not expect that the equivalent of convex smoothness will be enough. Not for the discrete scheme. There must be some extra assumptions to be found. And that's like why I would say one of the many reasons why acceleration is tough and hasn't fallen yet.
Thanks.
So let's see if anyone has any other questions. But I have a question. So something that caught my attention was when you were talking about the gradient descent with cost, you mentioned a hypothesis of the cost being minimal on the diagonal, right?
Yeah.
But on the later part, for the EVI stuff, the hypothesis was that the cost is dissipative, so you have that CXX is always zero,
Yeah.
which is stronger. So I would like to ask if you could expand on the difference between those two assumptions, because
so there isn't so much difference in it. So that basically, if the cost function is lower bounded, you can always like subtract the lower bound, kind of. So in terms of iterations, in a lot of cases, you will not see a difference between a cost and a translation of the cost. And when I say translation is when you add just a function either of x or either of y. I think function of y will be the one that is the least damaging in most contexts, but function of x you could do in some contexts as well. So that's my personal answer, as in you can translate a cost. Being zero specifically is not necessarily important. Being non-negative, this is crucial for the implicit scheme. So basically, if you remember over here, I replaced this thing by a cost function. To be allowed to do this kind of operation, I have to be non-negative. Or I have to add something non-negative. So that's why non-negativity has to do with the fact that I'm descending. So if you dropping non-negativity is like hard, you can rather drop it actually for you can drop it easier for explicit schemes than for implicit schemes. For explicit, basically what will happen is you have a bound of the form C plus F minus C. So you see there is C minus C. So those things compensate. Whereas if F equals 0, you also get a C minus C. That's true. C minus infimum of C, basically. So it's quite in the direction I was saying of like a translation, but you have to add something non-negative to G. That's the important bit. Then about the fact that you are zero, that you're only zero on the diagonal. Well, I don't think it's always necessary. I think it's a really greatly simplifying assumption.
Yeah.
Because basically it will make sure that your iterates are unique, that you don't have to manage the fact that there is a specific choice of elements in the subdifferential or things like that. So it simplifies your life greatly. We chose not to do it in infinite time in the gradient flow setting, but we did it in the finite. So maybe not in the paper that is online, but maybe in the next version, but probably yes in the paper online. Yeah, in continuous time, we were already dealing with enough troubles that we put that y was equal to x, and we removed the infinity values of the cost functions. But those are not major problems, I would say.
I see. So just to be clear,
Necessary, it's redoable.
so when you say that the cost is minimal in diagonal, it takes the same value in all the diagonal, or it can change? Because in that case, that in the
It
lower
can
bound is
It can change. Like
okay.
you can see it already from this expression, kind of. Like if you take f equals 0, let's focus on implicit schemes.
Uh-huh.
You see that your cost, you have a cxy minus infimum of c.
Mm-hmm.
So I'm not asking for the infimum of c to be constant and equal to 0.
I see.
So you can just subtract the infimal value. That will be completely fine.
Okay, thank you very much. So we are out of time. So we will thank again Pierre for this very nice talk. Thank you very much. And thank you all for coming. So the next session of the seminar will be on next week. So we will send the information and the invitation in the coming days. So thank you very much, everyone.
And Francisco, I stay. If you
Yes.
for any